Welcome to this explainer. Let's jump right in, because today we are completely demystifying computer programming. We're going on a trip from the absolute dawn of code straight through to how you can become a digital creator yourself using an incredibly fun visual tool called Scratch. If you've ever wondered how the digital world around you is actually built, you are definitely in the right place.
To make this all super easy to digest, we've broken the explainer down into 6 key chapters: the dawn of code, the programmer's workflow, language evolution, the pillars of logic, mastering Scratch visual coding, and finally, the art of debugging. So let's get into it.
Chapter 1. The Dawn of Code. Let's look at the historical foundation.
Before we even think about writing software, we gotta ask, where did this massive digital revolution actually start? Well, we have to go way back to 1948, to a machine affectionately known as the baby computer built at Manchester. This thing was a literal game changer, the very first digital computer that could run a stored program. It was all driven by mathematician John von Neumann's late 1940s concept of keeping instructions stored internally right inside the machine. Believe it or not, this is basically the granddaddy of the smartphone you're probably holding right now.
Now, to really get this, we need to nail down our terminology. What's the actual difference between a program and software? Well, a program is just an ordered sequence of instructions telling a computer to do one specific task. Easy enough, right? But when you bundle a whole bunch of those programs together to pull off larger, more complex tasks, usually with a user interface, boom, you've got software. Think about Microsoft Paint. That is software made up of tons of tiny programs that let you pick colors, grab a brush, or draw a perfect circle.
Moving on to Chapter 2, the programmer's workflow. Time to systemize the build.
So now we know what software is. How do we actually build it systematically? Every solid piece of software follows 4 exact blueprints. First up, you analyze the problem. You take a massive, complicated issue and chop it down into smaller, solvable subproblems using algorithms. Second, you design the program, mapping out the journey with things like flowcharts. Third, you actually write the program. This is the coding phase. And fourth, the one beginners always forget, document and maintain. You literally have to leave detailed written notes and comments in your code so that you or some other programmer can actually understand and fix it down the line.
Chapter 3. The Evolution of Programming Languages. We are going from ones to words.
Now, you might be thinking, how do we actually write these instructions? I mean, computers are literally just electrical circuits. Well, at the absolute bottom of the language hierarchy, we have machine language. This is strictly numbers, ones and zeros representing electrical states of on and off. It's what the hardware speaks, but let's be real, it's a total nightmare for humans to write. So we leveled up to assembly language. This was a great intermediary step where programmers could use short names for memory locations instead of pure numbers. But the massive breakthrough? That's at the top, high-level languages. These are written a lot like everyday English text, making them incredibly intuitive for us to use.
And this timeline lays out that leap perfectly. We started with those initial mathematical theories back in the late 1940s, and then, boom, a massive explosion of progress in the early 1960s. That was when high-level languages saw their first widespread use, and it completely revolutionized programming. Suddenly, a programmer could develop way more complex software with way less effort. It absolutely skyrocketed the speed of technological progress.
But there's a catch here. At the end of the day, computers still only understand binary, just those ones and zeros. So how do they read our fancy English-like high-level code? Well, we rely on some truly brilliant tools called translators, specifically compilers and assemblers. These are specialized programs, and their only job is to take your human-friendly code and translate it all the way back down into the raw machine language that the computer's processor can actually execute.
Which brings us to Chapter 4, the pillars of logic. Let's construct the flow.
With our languages translated and ready to go, we need to talk about the actual logic constructs that control how our software flows. No matter what programming language you choose to learn, your logic is always going to rely on 3 foundational pillars. First is sequence, literally just executing instructions one after the other, kind of like following a step-by-step recipe to make a cup of tea. Second is selection. This is all about decision-making. We use if, then, else statements, basically telling the computer, hey, if this number is even, do this. Otherwise, do that. And the third pillar is repetition. I mean, why do a task 100 times manually when you can just write a loop? Loops repeat a specific instruction automatically until a certain condition is met.
Now, inside those logic constructs, we have to store our data. And we do that using constants and variables. A constant is exactly what it sounds like. It's a value that is set in stone. It never, ever changes while the program is running. A variable, though, That is a named memory location that acts as a dynamic container. It holds data that shifts and updates while the program executes, like tracking a player's score in a video game.
And here is a really crucial point. When you write all this logic, you have to follow strict grammar rules, which in coding we call syntax. If you break those rules, like say missing a simple punctuation mark, you get a syntax error, and your program just completely crashes. But if your grammar is absolutely flawless, yet your program spits out the wrong answer, like it adds when it should have subtracted, you've made a logical error. The computer did exactly what you asked it to do, you just asked it to do the wrong thing.
Chapter 5, Mastering Scratch Visual Coding, the Magic of Drag-and-Drop Creation.
All right, let's step away from the abstract theory for a minute and look at how all of this comes together in an incredibly accessible environment called Scratch. What's amazing about Scratch is that it totally removes the fear of making a syntax error. No typing out complex code. It's a fully visual drag-and-drop interface. Over on the left, you've got your block categories. In the middle, you have the script area. That's your workspace for building logic. And on the right is the stage, where your code actually manipulates the characters, which Scratch calls sprites, just like that little orange cat you see right there. So instead of memorizing text commands, you're just snapping together intuitive puzzle blocks, and they're all color-coded by category. The blue motion blocks handle movement. The looks blocks can change your sprite's size or pop up a speech bubble. Sensing lets your program detect its environment, like asking the user a direct question. And the operators blocks let you do math or compare numbers. It's so intuitive.
And check this out. This perfectly illustrates our selection construct in action. We're using an orange if-then block, bundled with a green relational operator block. It's actively checking a condition. If the variable age is greater than 65, then trigger a visual response, making the sprite literally say, "You can retire." It is the exact same logic you'd find in professional, high-level languages, just visualized beautifully. And it works exactly the same way for our repetition pillar. You can just grab blocks from the control drawer to effortlessly build loops. Need a finite loop? Grab the repeat 10 block. Want an endless loop? Use the forever block to continuously run whatever is inside it. Or use a repeat until block to keep an action going until a very specific condition is finally met. It makes building complex game mechanics or animations so incredibly straightforward.
Finally, Chapter 6, The Art of Debugging. Time to fix the plumbing.
Because let's face it, whether you are dragging blocks in Scratch or typing raw text, no program works perfectly on the first try. Enter debugging. Debugging is the process of hunting down and fixing the bugs or errors in your software. And listen, it is not just randomly tweaking code and crossing your fingers. It is a rigorous, highly complex, and essential cycle to ensure your software actually performs without malfunctioning.
To do it right, you really have to put on your digital detective hat and follow these 6 exact steps. First, identify what the actual error is. Second, scan through the code to find the exact location of the glitch. Third, analyze why it's happening. Fourth, prove your analysis by testing it. Fifth, and this is absolutely vital, cover lateral damage, meaning you have to make sure your fix doesn't accidentally break some completely unrelated part of the program. And finally, step 6, fix and validate, running tests to confirm that bug is gone for good.
So, we've covered the history, the workflow, the pillars of logic, visual coding, and even debugging. But why does all of this actually matter? Well, as our source material wisely points out, many young people continue to be digital consumers rather than creators, and that is the absolute core takeaway of this entire explainer. You have a choice. You don't have to just passively consume apps and websites. With the logic pillars we've learned today and accessible tools like Scratch right at your fingertips, are you ready to stop consuming and start creating? Thank you so much for joining us, and we'll see you in the next explainer.